The natural log function. Specifically, now that we've discussed this thing called the exponential function, we're going to talk about the natural log function. And hopefully you recall from some point in time in the past, there's this thing called the natural log function. So, what is that function? That is, y is equal to ln of x. Now, I said specifically ln of x because this is not a product, this is x is being plugged into this thing called the natural log, ln. Now, what does the natural log function do? Specifically, what you need to understand is that natural log is an inverse function. And specifically, it is the inverse of the exponential function e to the x. Alright, what does all that mean? That means that if I'm trying to talk about what y equals ln of x is actually meaning, the definition of y equals natural log of x is really x is equal to e raised to the y. When you read ln of x, there is a question being asked. ln of x is asking the question, e raised to what power y gives us x? And so when you write this, y equals natural log of x, you can also rewrite that as x equals e to the y. Alright, so then there's a couple properties that pop out automatically, and specifically this first one, ln of 1. Well, what is ln of 1? Well, understand that if you write ln of 1, what you're really asking yourself the question is 1 is equal to e raised to what power y? Alright, e raised to what power y gives us 1. Well, specifically the answer to this question is y is equal to 0. So natural log of 1 is equal to 0. That's because e raised to the 0 power gives us 1, which is the thing being plugged into the natural log function. Alright, so then I have the natural log of e. Alright, well, let's think about what ln of e is. ln of e, or the natural log of e, is asking you the question, e raised to what power y equals e? Well, notice that if you just write e, which is the thing being plugged in here, that's e to the first, right? So y is equal to 1. Therefore, natural log of e must be equal to 1. Here we have the natural log of e to the x equals what? Well, you could rewrite that. That's the same thing as saying e to the x is equal to e to what y? Well, natural log of e to the x is equal to, specifically, the power you raise e to get e to the x. Well, set the powers equal. That means that this answer has to be x. And specifically, if any power on e is being plugged into the natural log of e to any power gives you just the power. This last one, e raised to the natural log of x, what does that mean? Well, remember that I stated that the natural log of x is the inverse function of e to the x. And if you can recall from pre-cal, in general, if we have inverse functions, as long as we take into consideration properly domains and ranges, and I'm kind of glossing over that for the moment, it's true that f of f inverse of x should be x. Similarly, if you have inverses, f inverse of f of x should be x as well. And so specifically, the thing to recognize is that if I had some function f of x is equal to the function e to the x, then its inverse function, f inverse of x, is what I said previously, which is the natural log of x. And so that's really what's going on here. And so when I have e raised to the natural log of x, that is f of f inverse of x. And so what we should get is the input, which is x. And that's exactly what we get. Alright, so now all we want to do is we want to use our official definition up there, that is y being equal to the natural log of x is exactly the same as x is equal to e to the y. And so that double-sided arrow is usually called if and only if. It just means that they are absolutely equivalent. So if I have e to the negative x is equal to 3.2 and they want us to write x in terms of the natural log, recall that what we mean is that y equal to the natural log of x can be rewritten as x is equal to e raised to the y. Okay, so now let's place what we have here. So we have specifically, if I just rewrite the information that was given to me, that's going to be e to the negative x is equal to 3.2. So my y in terms of this statement is negative x, and my x in terms of this statement is 3.2. Just recognize I'm lining everything up. So then that's going to be negative x is equal to the natural log of 3.2. And so that's how we use the formal definition. And so then they want us to write x in terms of the natural log, and so really I need to solve this thing for x, but that just means I divide both sides by the negative, and so if I divide both sides by negative 1, I then get that x is equal to negative natural log of 3.2. And that's the solution that we're looking for. Alright, for this next one, we have that if natural log of 6 to the x is equal to 23, I want to write x in terms of the exponential function. So we're using our definition again. That is y being equal to the natural log of x is exactly the same thing as x is equal to e to the y. So I'm just going to line everything up again, rewrite it. I notice that natural log of 6x, so this is going to be ln of 6x is equal to 23. And so then if I want to rewrite using the definition, then x, that's the input of natural log, and so that's going to be 6x is equal to e raised to the thing the natural log is equal to, which is 23. And so then I get that 6x is equal to e to the 23rd. Once again, it says write x in terms of, and so we need to solve for x, so divide both sides by 6, and then I get that x is equal to e to the 23rd divided by 6. Now if we wanted an approximation, we could of course find it using our calculator, but all we were told to do was find this in terms of the exponential function. Alright, so for number 3, we're supposed to simplify the following expressions. Now, what I want you to remember is that we have these things called the power rules. And the power rules are going to dictate how we work with exponents. Okay? And so, power rules, exponent rules, whichever you want to call them, remember that there's some properties. And so if I have e raised to a power plus another power, this is e to the natural log of x plus natural log of 2, using the power rules, that's exactly the same thing as e to the natural log of x times e raised to the natural log of 2. Okay, but why did I do that? Because then recall that e raised to the natural log of something is something, whatever that something is. And so e to the natural log of x, that's going to be the same thing as x. And then if I have e raised to the natural log of 2, e raised to the natural log of 2 is specifically just going to be 2. And so my answer is 2x. So I've simplified that as much as possible. Now if I have e to the 6 times natural log of x squared, I'm really trying to play with the idea of e raised to the natural log of something leaves me with something. But remember that via the power rules, if I have multiplication in a power, that's the same thing as a power raised to a power. So I claim that I can rewrite this as e raised, and I'm going to put a bracket around e raised to the natural log of x squared, all raised to the power of 6. And so then I get this statement. Well, but then I have e raised to the natural log of x squared, but e raised to the natural log of x squared is specifically going to just leave me with x squared, but then that's all raised to the 6th power. And so then I have x squared raised to the 6th, but then via the power rule again, this is x to the 12th, 6 times 2. And so that's completely simplified. So now we want to solve equations that are written in terms of logarithms. And the truth is we're going to just use a couple properties that we should recognize. And so first off, let's deal with this 5 natural log of 6x minus 7 is equal to 0. Well, I claim that if we can get the natural log by itself, then we can use our official definition of natural log to rewrite it in terms of an exponential, and hopefully we can solve it. And so let's try exactly that. So let's isolate the natural log as much as we can. Let's add 7, add 7. I then get 5 natural log of 6x is equal to 7. Then I can divide by 5, then I can divide by 5, and I get that the natural log of 6x is equal to 7/5. But then I want to remind us officially what is the definition of natural log. That is, y being equal to the natural log of x is exactly the same thing as x is equal to e raised to the y. And so then notice that the stuff input into the natural log would be by itself, so this is then 6x is equal to e raised to the stuff the natural log is equal to, so that's e raised to the 7/5. Then at this point, if I divide by 6, I get that x is equal to e raised to the 7/5 divided by 6. And I claim that is the solution. If we want to find an approximation, if we were told to find an approximation, we could find an approximation just by plugging this into our calculator. But since no one said approximate, this is the solution. The next one, we have the natural log of x squared plus 4x plus 11, where all of that polynomial I just stated was inside the natural log, is equal to the natural log of 6x plus 14. When you see this, what I want you to understand is that the natural log of something being equal to the natural log of something else means you let that something and something else be equal. And so, but that's only if we have a single natural log. And we'll have this issue helped by our next section. But specifically, I can just drop the natural log and I can say, okay, that's x squared plus 4x plus 11 is equal to 6x plus 14. At this point, we can then solve. So I see I have a quadratic form, so I'm going to put everything on one side. Minus 6x minus 14. I then get that x squared minus 2x minus 3 is equal to 0. I see that this factors really quickly, and so this is then going to be x minus 3 times x plus 1 is equal to 0. We can double check that. 1 times negative 3 is negative 3. X times x is x squared. Negative 3 times x is negative 3x. 1 times x is 1x. Negative 3x plus 1x is negative 2x. That works out. Then via the zero product property, I get specifically that x minus 3 is equal to 0. X plus 1 is equal to 0. And so plus 3 plus 3, x is equal to 3, or x is equal to minus 1 minus 1, x is equal to negative 1. And so I get these two possible solutions. Now, one thing that is important, and specifically if you look back at initially what I stated when we wrote down what a logarithm function is, it's only defined for values that are positive that get plugged into the exponential function. The values that get plugged into a natural log have to be positive. If they're not positive, it's not defined. And so for this 3 and this negative 1, I need to double check that they work or don't work. And so I actually need to plug them back into my initial equations, but I can kind of ignore the natural log. I can just plug them into there and there. Well, notice that when I plug negative 1 into 6x plus 14, 6 times negative 1 is negative 6, negative 6 plus 14, that's going to be positive, that's fine. 3 plugged in there works as well. I do need to plug it back into this quadratic to confirm that it's okay, but I claim when we plug the positive in, we're going to have no issues. And I also claim that if we plug in negative 1 into x squared plus 4x plus 11, we're also going to get a positive, and so we're perfectly fine. And so both of these are our solutions. We have no issues here. But once again, I just want to state that if you find solutions for natural log functions or logarithm functions of any variety, you do need to confirm that if you plug them into any polynomials being plugged into the natural log, you have to be strictly greater than 0. That means if you get 0, it's out. If you get a negative inside the natural log, it's also out.